So today I'm going to talk about how natural language processing, or NLP, has been applied to advanced clinical excellence and some of the state of the practice opportunities, and along with some challenges. So before diving into the topic today, I'd like to introduce some facts of nowadays AI. So artificial intelligence is one of the most interesting field of research today. Actually, not only in academia, but also in industry, particularly in healthcare industry in the recent years. AI has become a hot topic and attract a lot of investment. There are a lot of healthcare AI startups recently. And particularly due to the outstanding performance and the recent advances in deep learning. So a lot of successful applications of deep learning in real world products. So for example, if we are using iPhone today, whenever we use our face to analog iPhone, actually run deep learning models on the back end to analog the iPhone. So those deep learning techniques has been really applied in those products and has been very successful. And we all know that Turing Awards was given to 3 pioneers actually in deep learning in 2018. So language is the most compelling manifestation of intelligence. Human language is the most complex behavior on the planet, and humans' intelligence allows us to have language. So if we can teach computers to fully understand the language, write the language, speak the language, and generate the language, then computers may have the intelligence, but we are still very far away from that. You may also be curious, what is the relationship between NLP, AI, machine learning, and deep learning? So this figure shows the relationship between those fields. As we see here, the NLP, machine learning, and deep learning is totally a subfield of AI. And a lot of people actually think NLP is AI complete problem. So that means NLP is totally an AI problem. And deep learning is a subfield of machine learning. And there's some overlap between NLP and machine learning and deep learning, but there are also some that's not overlapped with machine learning. So those this area actually comes from computational linguistics, from the computer science domain. And the overlap between NLP and machine learning is actually due to a lot of NLP tags can be formulated as a machine learning problem. So for example, text classification, sentiment analysis, those techniques actually could be formulated as a classification problem that could be solved by machine learning. That's where those overlap come from. And the overlap between NLP and deep learning is mainly due to the recent advance in language models, such as transformers, BERT, XLNet, those deep learning, those neural networks. So we all know that electronic health record is a longitudinal record of patient health information generated by each clinical visit. So following the High-Tech Act law in 2009, many healthcare institutions adopted EHRS. So nowadays, I think almost 100% of the hospital in the US has adopted EHR data. And the size of the EHR data actually increased dramatically in the past decades. So if we want to promote AI and promote NLP in the healthcare domain, we have to, we all know AI is a data-driven approach. So we have to leverage all the information available from EHRs. But the reality is a lot of EHR data is unstructured. So based on a recent study, 80% of the EHR data is unstructured. So for example, clinical notes, patient provided information, family history, radiology reports, those are all unstructured EHR data. And only 20% of the EHR data is structured. So for example, demographics, lab tests, medication, diagnosis code. So therefore, NLP is a key technique to deliver better care through data. So which is actually the goal of health informatics. So what is NLP? So I talked about NLP, but what is NLP? So let's look at the definition from Wikipedia. NLP is a subfield of computer science, information engineering, and artificial intelligence concerned with the interaction between computers and human language, and how to program computers to process and analyze the large amount of natural language data. So here I want to emphasize several keywords. NLP is a multidisciplinary field that combines computer science, information engineering, and AI. And NLP does not only process large amount of data, but also analyze large amount of language data and extract the nuance from those large amount of language data. And then I want to talk about several examples about NLP. So you can get a feeling, get an understanding what are those NLP applications, and actually we are using those applications in our daily life. So NLP is about question answering. So we all know that IBM Watson is automated question answering system. It competed against Jeopardy's two great champions in 2011. And we are using question answering system through those voice assistants in our daily life, like Apple Siri, Microsoft Cortana, Amazon Alexa. And it is not uncommon people nowadays are using Amazon Alexa to purchase product. And now we have a smart home, and we're using Alexa to control our thermostat and all the temperature and everything in our home. And all of those techniques, voice assistant is running question answering system on the back end. NLP is also about information extraction. So here is an example. So this is a sentence from a clinical note. And the sentence is, the patient's maternal grandmother was diagnosed with breast cancer at age 59 and passed away at age 80. Because a lot of family histories are documented in this free text, so we want to extract the family history from the clinical notes. And the extraction process is called information extraction. And in this example, the first thing we need to do is to identify the entity from the text data. So for example, what is a family member mentioned in this text? What is the condition? What is the age? So we call this step named entity recognition, or NER. And then we also need to normalize those entities after extracting the information. So for example, we normalize the maternal grandmother to family member, and then normalize living status to those normalized concept. After normalizing those entities, we have to relate those entities. So because we need to know what is the age associated with the condition, what is the age associated with the living status, and what is all of those condition and living status which family member is associated with this. So we call this relation extraction. We have to extract the relations between those entities. And then finally, we build something like a knowledge graph. So that shows the whole picture of the patient family history. NLP is also about a sentiment analysis. Actually, we are also using this every day. Like whenever we purchase a product from Amazon, we check their attributes, whether those attributes meet our needs. But most often, we also check the review comments, like whether there are more positive review comments or negative review comments. And actually, those review comments impact our decision to buy the product or not. And nowadays, those sentiment analysis has also been used to improve the quality in a lot of hospitals. And a lot of customers, when they choose like primary care physician, they also check the comments or review comments to those physicians, and then choose the physician they think that meet their needs. So analyzing those comments is called a sentiment analysis. NLP is also about information retrieval. We are using that every day as well through those search engine like Google. Whenever we type a query, Google runs those information retrieval system to retrieve the relevant documents that are related to our input query. And after Google just developed a EHR system. So the whole EHR system is an information retrieval system. So any healthcare provider can type in the information need in the EHR system, and then the system will find the EHR information that those health providers are looking for. So the whole EHR system is like a information retrieval system. So traditionally, NLP can be categorized into two categories, or one is the symbolic NLP or rule-based NLP. So this technique is like developed 3 or 4 decades ago. And since we are entering machine learning and deep learning era, a lot of techs has been using machine learning and deep learning techniques to solve those NLP tasks. A lot of people may ask, what is the right approach for any project? So it's really not about selecting a fancy technology. It doesn't matter if you select deep learning. You have to select deep learning or machine learning because it is fancy. It is more about understanding the strength and weakness of the nature of the project, and particularly the strength and weakness of those techniques. So, for example, for the rule-based NLP techniques, the data we have is input data and a lot of human-crafted rules, and we use the input data and those rules to get output. But for the machine learning and deep learning-based NLP techniques, we have input and output first, and then we use those to train machine learning model to automatically learn the rules. So then what is the right approach? So actually there are different perspectives when we look at this problem. So there is a data perspective. So if we have a lot of data and a lot of annotated data, a lot of gold standard, machine learning and deep learning techniques usually have a better performance. But if we have only a small number of data and a small number of annotated data, which is actually very common in clinical domain, we usually use those rule-based or dictionary lookup, those rule-based approach. Another perspective is a user perspective. So for example, if like a physician or those clinician, if they are looking for a more interpretable approach, then we tend to use those rule-based approach because it's very easy to interpret what is going on inside the model. But if people are okay with a less interpretable and less customizable approach, the machine learning and deep learning approach are usually used because those technologies are always viewed as a black box. So we don't know what is going on inside the model. A lot of time, actually, we is a hybrid approach. We consider both a data perspective and a user perspective. So the rule-based NLP is not the focus of our today's topic, but I would like to walk through the pipeline for those rule-based NLP to give you an idea what the rule-based NLP look like. So usually we have text. We have the text data from clinical notes, and in this example, we want to extract the gene mutation from the clinical text data. So the first thing we usually do is to detect the sentences in the clinical text. In this case, there are 3 sentences. The next step is called tokenization. Tokenization means we split the sentence into words. And in this case, we split the first sentence into those words. So for English, it's very trivial. It's very easy to split because each word is separated by a space. However, for a lot of other languages like Arabic language or East Asian language like Japanese or Chinese, tokenization may be very challenging because there's no space between words. So after tokenization, we identify the concept from the sentence. So in this case, because we are interested in the gene mutation, so in this case, this is P53. This is the concept we try to extract. The next step is called assertion, because it is not uncommon in clinical text. There are a lot of negated mention. There are a lot of hypothetical mention. So for example, physician may say that this patient is a hypothetical depression, has a hypothetical depression, or possibly have some certain disease. So we have to extract that kind of concept. And we call this step assertion. And in this case, this is a possible mention of the gene. The next step is to apply several manually crafted rules to extract the concept, because there are a lot of different ways to write the same concept. For example, in this case, P53 is split by a space, but in a lot of cases, P53 comes in as one word. So we have to consider all of those and write those in rules. Then we use the rules to extract this concept. So in this case, it's P53 mutation, and this is a possible mission. And in order to evaluate the NLP system, we usually need to do a manual chart review and create a gold standard, and then evaluate NLP system. On the left-hand side, all of those components is an NLP system. So for the statistical NLP, we usually use machine learning techniques and deep learning techniques. So for the machine learning techniques, we all know that the machine cannot consume those text data. So we usually use the features to represent original text data. So for what I mean by features, for example, the number of words in the text or the word frequency in the text data. We use those features and represent the text in a something like Excel sheet to represent the original text. I use that numbers in the machine learning model to train the machine learning model. So deep learning, as opposed to the machine learning technique, deep learning actually could automatically learn those representations. So we do not need to worry about what feature we want to extract, because deep learning use those neural networks to automatically learn the representation, and then use this representation for any downstream applications. So that's why deep learning technique is always called the representation learning, because they try to learn a representation of the original text data. So you may also curious how to represent the natural language in computers. So we all know that natural language text can be viewed as a sequence of discrete symbols. That's a sequence of words. So for example, I love NLP and I like dogs. So traditionally, we use a model called a vector space model to represent the natural language, the text data. So first, we assume a bag of words. That means all the vocabulary words comes from bag, and all the vocabulary words are independent from each other. So we are actually picking the word from the bag according to the sentence. So by using that kind of representation, we can use the whether this word occur in the sentence or not to represent the word. So for example, I love NLP and I like dogs, and those occur in the sentence, and we can use 1. If the word does not occur in the sentence, we use 0. So using this representation, we can represent those words using 1 and 0, so that we can input those in the computers. However, there are a lot of problems with this representation. The first problem is very sparse. So there are a lot of zeros in this representation, so which will consume a lot of memories in our computer. The second problem is this representation actually loses the semantic meaning of the words. So for example, we all know love and like, they are synonyms, but if we compute the similarity is 0. So using this representation, this simple representation, although computer can compute those language, but the semantic meaning is missing in this representation. So that's why computer scientists and linguists, they propose a lot of language models. So they try to use those language models to learn the meaning of the words using dense representation. So like a decade ago, people called this dense representation or semantic representation. And nowadays people call this word embedding. Actually, it means the same thing. So basically we are trying to use values and numbers, those dense representation to represent the word. So using this representation, if we calculate love and like, then the similarity is not 0 anymore. And if we calculate like a love and NLP, the similarity between love and NLP is smaller than the similarity between love and like. So that's essentially what dense representation means, because this representation captures the semantic meaning of the word. So if we think about this, if we can learn, if we have a large corpus, so for example, all the text data available in the internet, and we train a model and go through the large amount of text data, so the model may be be trained and learn the semantic meaning of the word through those large amount of data, right? So actually, this is exactly the same idea behind those deep learning models. Any deep learning models try to learn a better semantic representation, and hoping those semantic representation could represent the semantic meaning of the word. That's why I always say NLP in AI is all about learning a better representation of the language. And the question is how? So we all know the images are very easy to represent because each image can be represented by a lot of pixels, and each pixel can be represented by RGB values, which is a 3-dimension. But language is much harder. So here I give 2 examples. So first example is the weather looking gloomy today. So I want to ask, what is the sentiment about this sentence? So actually, this sentiment about this sentences is highly impacted by the context, or highly impacted by the person who speaks this sentence. So here are 2 examples. In the first example, the weather looking gloomy today, I better wear my trusty rubber boots. So the person who speaks this sentence actually have a positive feeling about the weather. And the second case, the weather looking gloomy today, I'm going to stay inside. So obviously the second person had a lot of negative feeling about the weather. So even though this sentence, the word in this sentence is exactly the same, but the semantic meaning of this sentence actually highly impacted by the person and by the context of this sentence. So the second example is will. So in this sentence, there's only one word will. So can you tell what is the meaning, semantic meaning of this word? So it's very challenging to tell because each word has a different meaning in this sentence. So for example, the first will is a person, and second will is a future tense of the verb, right? And the third will is a second person. So as you see here, language is definitely more than 3 dimensions. It's actually a high dimensional space, and it's very difficult and very hard to represent the language. That's why a lot of deep learning models try to represent language. So, and then in the following, I will provide 2 use cases of how the NLP has been used in clinical domain. The first use case is we try to use NLP to identify major depressive disorder phenotypes from clinical notes. So here is a little bit of background why this is a significant problem. So major depressive disorder, or MDD, it is a prevalent psychiatric disorder, but a lot of MDD phenotypic information is documented in free text EHR data, and especially in primary care setting. NLP need to be developed to extract such MDD phenotypes from clinical notes. So the goal of this project is try to identify MDD phenotypes from clinical notes, and we formulate this as the sentence level identification or sentence level classification. That is, we try to classify each clinical note sentence into one of the categories, like positive MDD, negated MDD. There's 4 categories: possible MDD and NO MDD. Those 4 categories, and for the traditional rule-based NLP, if we want to develop a rule-based NLP, first we retrieve those clinical narratives, and then we annotate those clinical narratives and create gold standard, and then use the gold standard to develop the rule-based NLP system. When we develop the rule-based NLP system, we usually check those ontologies and terminologies from knowledge base, and also chat with the human expert, because those experts, they write those languages in clinical notes, and this will give us a lot of information that is not available from those knowledge base. And after developing the rule-based NLP, we evaluate the NLP system on the gold standard. So as you see here, there are a lot of efforts actually involved in this process. First is we need experts' knowledge, expert experience, and we also need to examine all those knowledge bases. Second effort is knowledge engineering. That means we need to manually craft a lot of rules, and sometimes it's very time consuming because there may be hundreds of rules for one concept extraction. The third is annotation. We need to annotate training data for the rule-based NLP. So as we using those conventional machine learning model, we're hoping machine learning model could automatically pick up those patterns, pick up those rules. But still, when we train the machine learning model, there are still a lot of human efforts involved. For example, we need to engineer the features, what features we need to use as the input to those machine learning model. And secondary, because machine learning model is data hungry models, we need to annotate large amount of training data. So that's why this is a pipeline, clinical NLP pipeline we propose. We call this distant supervision. So actually, this is more like a weak supervision. So first, instead of manually creating a lot of gold standard, we try to use simple rule-based NLP to create a gold standard. So because this gold standard is created by NLP, this is not a real label. That's why we call this weak labels. And also because this can be done by the NLP algorithm. So the weakly labeled clinical data could be as large as possible because it's a machine who create those labels. And then we try to use those clinical data with a weak label to train the machine learning model. And instead of using a lot of manually crafted feature, we use a word embedding feature, so which is learning from deep learning, so that this word embedding feature can be used in the machine learning model. We don't need to care about the feature extraction or feature engineering. And finally, we test the machine learning model on some async clinical data. So this is the pipeline we proposed. And since we have a lot of deep learning neural language model available, so we are actually curious how those neural language model perform in this pipeline. So then instead of using those word embeddings features, we are using those neural language models because those neural language models are pre-trained on a large set of data, and all the features and all the weights has been pre-trained and embedded in those architecture. So we can directly use those neural language model and fine-tune on the weakly label. And we are curious how those fine-tuned model perform on this clinical NLP pipeline. So this is those are the models we tested. We tested BERT and bioclinical BERT. So BERT is a pre-trained Wikipedia and book corpus, and bioclinical BERT, in addition to those corpus, bioclinical BERT also pre-trained using mimic data. So it carries some clinical language characteristics. And both models are fine-tuned on our weakly labeled clinical notes for MDD identification. And in order to compare with the traditional model, we tested three baseline machine learning model: random forest, K-9 and support vector machines. And for the data, we actually we first identified the case patient and control patient using those ICD code, and then we retrieve the clinical notes for those patients. So for those patients, we have around 170,000 clinical notes, and also because we want to know the real performance of those of the pipeline we proposed, so we actually create annotated data set for the testing data. So in the testing data, there are 500 clinical notes. So finally, in the training data, weakly labeled training data, we have around 110,000 sentences. And in the gold standard testing data, we have around 30,000 sentences. And this is the result for the MDD identification using different models. So this result indicates the bioclinical BERT achieved the best performance among all the models. So actually this is consistent with our hypothesis because we think bioclinical BERT carries some clinical language features. So that's why it should perform better. And both BERT models have better performance compared to the traditional machine learning model. And actually BERT is, the performance of BERT is comparable to bioclinical BERT when it tried to identify the positive MDD actually it's not as good as the bioclinical BERT. We try to identify a possible MDD and negated MDD. So the second use case is for digital phenotyping for clinical trial recruitment using information retrieval, which is also an NLP technique. So we all know this is a typical clinical research pathway. So whenever a clinical researcher or physician, they have a question, clinical question. So if they try to answer the question, the first step would be designing a protocol. For example, design the clinical study protocol or design the clinical trial criteria. And then they will try to identify whether there is enough patients for their study. So this step is called a feasibility study, whether this study is feasible in that location or in that site. And then after prove their study is feasible, then they will identify those patients and then recruit those patients or human subjects into the study and then give them some new treatment or intervention and then collect the result and analysis. So as we see here, there are actually key components in this pathway, whether this clinical study will be successful or not. One is a feasibility study. So they have to approve that there is enough patients. So if there's no enough patients, they have to redesign the protocol. And this is also the critical step for any study that try to seek funding. And second is the patient identification or patient recruitment. They have to recruit enough patients in the clinical trial. However, a lot of clinical trials actually fail because they cannot find enough patients. They cannot recruit enough patients. So according to a recent study, 85% of the clinical trial fail because they fail to retain enough patients. And only 3 to 5% of the cancer patients participating in cancer clinical trials, even though up to 20% of patients, they are eligible. So we have a lot of patients, they have clinical data, EHR data in our database. So we try to find eligible patients among those patients and give them recruit them and give them new treatment. So we try to leverage the data, the EHR data in the database, and then develop a pipeline using NLP and AI to automatically filtering those patients that are not eligible to the clinical trial using the data in our database. So using this process, we are hoping it could facilitate and accelerate those clinical trial recruitment. So this is a real world project. And first, usually at the beginning, we are given a lot of clinical trial criteria. And those criteria or protocol, they are written by those researchers. As you see here, always they have inclusion criteria and exclusion criteria for the patients. And the first step we usually do is map those criteria back to the data in our data warehouse. So for example, what are the diagnosis code for those criteria and what are the medication code or what are the CPT code for those procedures? And a lot of time, there are several criteria that cannot be handled by those structured EHR data. So we have to develop another NLP pipeline to process those criteria that requires clinical text data. So that is the architecture or that is a pipeline of the current solution. We use the structured data to filter patients and then post-process the patients using their unstructured data to filter out those patients that does not meet the criteria. However, we are hoping that we could develop a system that could put all the unstructured data and the structured data all together in one place so that we can filter those patients or identify those patients in one place. So when we think about this problem, actually we think this is very similar to an information retrieval problem. So in information retrieval, we have the user's need and the user input the query into a search engine. And search engine will search a collection of documents and retrieve the relevant documents. And in our case, instead of a collection of documents, we have a collection of patients. And instead of retrieving relevant documents, we try to retrieve relevant patients. So that's why we try to adopt the information retrieval system in this cohort identification problem. So this is a tool we developed. I'm not going to into the detail of the tool, but I want to emphasize that we put both structured data and unstructured data, both information stream from those from EHR in the system. So the system uses machine learning and information retrieval techniques to combine the information from both data channel and then retrieve the cohort. And this is some interface we developed for the tool. It's very similar to a search engine. A user can input the searching criteria, and then the search engine will return those patients and documents, and rank those patients and the documents according to a similarity score. So it's very similar to search engine. So there's also another way of thinking about the cohort retrieval, which is patient representation. So because each patient is represented by the EHR data, can we train some machine learning model and or AI model to learn a patient representation? So this patient representation is very similar to word embedding. So we can represent each patient using those semantic representation. And for clinical trial, we can actually first identify some target eligible patients, and then we compare the similarity between those target eligible patients and those patients in our database. And then maybe we can find more similar patients. And the first attempt to solve this problem, so as you see here, because we have no labels for this problem, so that's why we have to adopt like an unsupervised machine learning model. So this is the first attempt we try to solve this problem. We try to use unsupervised machine learning to learn the patient representation. And we actually used a topic modeling to learn those patient representation. So a beauty of the topic modeling is that we don't only learn the patient representation, we also learn the disease representation from the topic modeling. So for the patient representation, we can actually put those patients, we can represent the patient in a vector format, and then cluster those patients into subgroups. So for those patients in each subgroup, they share very similar disease trajectory and characteristics. So we can apply those personalized care or personalized precision medicine for those patient subgroups. And in addition to the patient subgroup, we can also identify the disease groups. And for the disease groups, actually those diseases within the same group, they share some similar characteristics, and we could use those disease subgroup to enhance the disease risk prediction, because it actually embed a lot of comorbidities information inside. And also we can discover some new underlying disease mechanisms using those disease clusters, because this is a totally a data-driven approach. And this is the topic modeling we use. So we use the traditional topic modeling, which is latent directly allocation. And we also propose a new topic model, which is called a Poisson directly model. So I'm not going into the detail. You can go to the paper for more details. But here I want to emphasize that unlike LDA, which use multinomial distribution to model the disease, in PDM we use a Poisson distribution to model the disease count for each patient. And also here we introduce a gamma distribution, because from the data we see a lot of patients, even though they are not some patients are sicker, of course, so they have a lot of diagnosis code. But some other patients, they are actually not sicker. They also have a lot of diagnosis code. That's because they have a better insurance. So they just tend to go to hospital more often. So they generate more diagnosis code. So we use this gamma distribution to penalize those patients who have a significant large amount of diagnosis code. So this is some detail of the method. And this is the result. So we compare the disease cluster identified by LDA and PDM, and we found LDA actually cannot identify those disease clusters, but our proposed model could identify those disease clusters. And we used the 3 data set to evaluate the performance. 3 data set for 3 different patient cohorts. And we also compared the survival curves of the patient subgroups. As you see here, actually, both LDA and PDM could identify those patient subgroups with very significant different survival curves. But we also check into the patient subgroup details, and we found LDA actually tended to split those patient subgroup according to those age and sex, because age and sex are statistically significant between those subgroups. But PDM, as we mentioned earlier, it actually clustered those patients not based on their age and sex, actually based on the real diagnosis of those. So actually this result is more interesting to epidemiology researchers, because they observe a lot of patients. For example, one patient is at 80 years old, the other patient is at 50 years old. And these 2 patients actually have a very similar biological disease. So they have a similar disease, even though their age and sex may be different, but their biological their body is already at the same status. So it's very interesting and also very important for this type of prediction. So that's why I always say that AI in medicine is all about learning a better representation of the patient. So if we can learn a better representation of the patient, we actually can have a lot of applications of this domain. So when we consider those patient representation, of course, we need to consider more data. So for example, nowadays, social determinants of health is very important. And if we can incorporate those social determinants of health in building patient representation, those patient representation may be more comprehensive and maybe more indicative for all the downstream applications. So since we are running out of time, I will briefly discuss some challenges in clinical NLP. The first challenge is the data. So because the clinical data has a lot of patient protected data, and because of HIPAA problem, we cannot share those data, and they are not mandated publicly available. The second problem is generalizability and portability, because those data cannot be shared across institutions, and each institution may adopt their own EHR system that may have different data standards. So you develop an AI model or NLP model in one institution, so it may not be portable or generalizable to another institution. So that is another challenge. However, it is true that there's no data available. Actually, I checked the public NLP corpus, and there are actually a handful of public corpora that is possible to access. So for example, we have those challenge data like I2B2 NLP challenge data, ONH NLP and track challenge data, and a mimic data set is also available. And there are also empty samples is publicly available, and a SIM corpus is also radiology and pathology reports is also available, and also meta-STS corpus. And all those data are actually available under data use agreement. It's very easy to complete those data use agreement and they get access to the data. So another problem, of course, is interpretation of those machine learning and deep learning problems. And this is even true when we want to apply this in practice, because like a physician and those clinicians, they're always wondering why the model produce false positive and false negative. And this, if there's error from the model, that will impact the decision-making, clinical decision-making, that will actually impact the healthcare for our patients. So that's more severe. So that's why interpretation of those model, it is actually a challenge and also an opportunity in this field. So another challenge in this field I didn't cover here is actually related to the social determinants and the bias of the model, because the model we developed may be biased towards a certain patient population based on the data we have. And the validation may also bias, because the validation data set may also bias towards a specific population, and that has bias for the underrepresented population. And also the model itself may also carry some bias. So there's another problem when we apply those techniques in clinical practice. And those are some reference, and you know, I'd like to thank you and answer any questions.